Hello, and thank you very much for the opportunity to present my talk here at the LISA Symposium 2022 and your interest in my talk. I would like to present you an idea for an initial reference sensor which might benefit future gravitational wave missions. My name is Alexander Schulze. I'm affiliated with Airbus in Friedrichshafen and the University of Ulm, where I'm currently finishing my PhD thesis. I'm very curious to hear your thoughts on this idea, and I'm looking forward to meet you in the discussion session after this talk. Let me give you a brief introduction into what is a gravitational reference sensor and why it would make sense to use a sphere as a test mass. A gravitational reference sensor comprises an object, the test mass, that is left freely floating to follow a geodetic trajectory. The GRS typically comprises of a cube or even two in the case of LISA. Spherical test masses have not been chosen for LISA, and I hope that with this new approach of a decelerated spherical test mass, I can mitigate some of the concerns that led to this decision. Spherical test masses in general can be advantageous in terms of performance. They offer a simplified design with only a single test mass. And there is not one fourth degree of freedom, hence the system offers 6 degrees of freedom drag-free attitude control. Further, the environmental noise is severely reduced. For instance, every noise source including residual gas, radiometer effect, and forcing noise are severely reduced or not present. The primary challenge in implementing a sphere as a test mass is the contribution of surface topography into the center of mass determination. Here, the error must be below the 3 picometers, which is the contributed budget error for the test mass interferometer. 3 approaches exist to mitigate this problem, which I will introduce to you now. Freely spinning spheres refer to the concept of not actuating the sphere at all, and leaving it with its initial velocity, for instance after the release. Here, surface topography corrections are required. For this reason, at Airbus, we investigate the a priori characterization of surfaces with novel picometer metrology approaches. This is due to the fact that current state of the metrology is not sufficient at mid-spatial frequencies. Another approach is the fast-spinning sphere. Here, the sphere is accelerated to a rotational rate of around 10 Hz. This shifts contributions of the surface above the measurement bandwidth. The new approach we propose here is to decelerate the sphere. We can show that surface contributions can also be shifted thereby below the measurement bandwidth. This is a rather simple approach, and we can show that it is compliant with the requirement. The velocity reduction necessary can, for instance, be achieved using revolving electromagnetic fields. On the top right, you see a figure where we have a Helmholtz coil assembly which is used to generate electromagnetic fields. Further, the attitude needs to be read out. This can, for instance, be achieved using local flat surfaces which are probed with additional beams. Here they are shown in green. The local flats impose a limitation on the angular freedom of a test mass, but then again, this is very acceptable. It is beneficial to have particular areas which are provided for GPRM holding and release, and if those undergo a damage, will not influence the measurement as those are never probed by the measurement beams. Let's take a look at the potential contribution of surface topography into the measurement. We see here a potential surface contribution into the test mass interferometer single link displacement error. This contributes defined by the surface spatial frequency and the rotational rate of the sphere. The underlying models here assume in the graphs that for the orange plot, the performance of state-of-the-art metrology has been applied and there has been a surface correction, and the velocity is equal to the release velocity of the mechanism. This corresponds to the concept of a freely spinning sphere. Here we can see that still we have a violation of the requirement at mid-spatial frequencies. The blue line represents a decelerated sphere, which means the sphere has been decelerated using electromagnetic fields, for instance, and then, even without surface topography corrections, only using a well-manufactured sphere, the underlying assumption here is a sphere manufactured to the precision as is gravity probe B spheres, we do not violate the requirement already. Two operational modes would be plausible for enabling a decelerated sphere. It must be ensured that the rotational velocity is slow enough. This can be done, for instance, continuously. As you require only very weak magnetic fields, this could be potentially enabled even within the limitations of a magnetic environment during the science periods. For instance, just a field of 100 nanotesla at a rotational frequency of 50 Hz is very sufficient to have enough torque to control the sphere. If there would be concerns with the magnetic environment, it is also potentially possible to not apply any magnetic fields during science mode. This is what we would call interval mode here. Then we have to look at potential other effects, which would be what are the DC torques acting on the test mass before we get too fast and have too much velocity and would violate the requirement again. Here again, it is very beneficial to have a sphere because on the sphere we will have very few torques acting, as it is very symmetrical and we now have a very improved self-gravity factor because we have a large gap and less local structure than would be required for a cubical test mass. To demonstrate the general principle of active deceleration with magnetic fields, we have built a testbed to demonstrate actuation with Lorentz forces by induced magnetic fields. The setup comprises a 3D Helmholtz coil assembly, a sphere with a local flat, and an optical readout. The sphere is mounted on a string, which just enables us to demonstrate it in one axis. There we were able to demonstrate 1D active position control and velocity reduction. To sum it up, spherical proof masses can be advantageous. They do have a better environmental noise performance and they enable true 6 degrees of freedom. But they face challenges. Our approach here is to use a decelerated sphere to break it down using magnetic fields. We have shown that this is feasible in terms of performance and that it's actually a very simple thing to do. We have demonstrated in a 1D experiment how this can be done. The next steps will be to translate this into a full 3D axis setup. This can be, for instance, done with the air bearing. And with the air bearing, then you can actually do a very nice characterization of the aero torques. Further steps possibly necessary are that you will need a grab and release mechanism designed for a sphere, as it is currently only done for a cube. In general, you'll find a more detailed description in my PhD thesis, which will be published by the end of this year. If you have any questions or remarks, I'm looking forward to meet you in the discussion session or hear from you via email.